I'd like to share with you a short presentation about Dyrobes, the world's most complete and advanced rotor dynamics software. Running machinery at thousands of RPM can lead to failures. Here are some examples of rotor damage that resulted from improper design or maintenance. Here's an example of a coupling failure caused by torsional vibrations. And this is the kind of catastrophic failure that can cost millions of dollars, thousands of working hours, and even lives. If you are an engineer in charge of the design, purchase, or maintenance of rotating machinery, you will want to understand and anticipate problems like these. To do so, you can purchase software that allows you to build a mathematical model of your system. In this presentation, we'll review how Dyrobes rotor dynamics software provides all the tools you'll need to build a model so you can anticipate potential failures and ensure that your machinery is operating at top capacity. For the practicing engineer, Dyrobes is powerful but also intuitive and easy to learn. Unlike other software currently on the market, Dyrobes is completely based in finite element analysis, allowing for more complex modeling and more accurate calculations. Dyrobes was created by Dr. Wenjian Chen, a leader in the field of rotor dynamics. Since 1991, when Dyrobes was introduced, it has been under continuous development. Dyrobes has an intuitive Windows-based interface. Today, it's used worldwide by engineers in industry, government, and universities to analyze and design steam and gas turbines, aircraft engines, compressors, pumps, turbochargers large and small, and for many other types of rotating machinery. One of the great advantages of Dyrobes is that it's comprised of 4 distinct but integrated modules. Dyrobes rotor is capable of linear and nonlinear analyses of free and forced lateral, torsional, and axial vibrations. Dyrobes bperf complements Dyrobes rotor by calculating bearings' steady state and dynamic performance of an extensive range of bearings. Dyrobes rotorbal is for rotor balancing. And with Dyrobes gear load, you can calculate gear and bearing loads on gear-driven assemblies. In Dyrobes rotor, it's simple to build a model. You start by selecting one of 4 units of measurement in either English or metric units, or you can specify your own system of units. You select your materials and then build your model by defining separate geometric elements by length, mass, and stiffness. As you build your model, you can check the results and see what you are building visually, which will help you build a more accurate model. You can add different types of discs to the shaft. Dyrobes gives you several choices of rigid and flexible discs. In Dyrobes rotor, you have many types of bearings to choose from to model your rotor. The bearings modules calculate the nonlinear force and the bearing force used in the analysis. With Dyrobes bperf, which we'll review in a few moments, you can make additional calculations such as the power load or flow requirements for your bearings. Dyrobes gives you many options for coloring and designing models so that they resemble the machinery on which they are based, which can be very important when you're making presentations to managers, designers, or clients. With practice, you can learn to model very complex machinery. Here are a few examples from Malcolm Leader, one of the world's leading rotor dynamics experts. Once you build your model, the next step is analysis. In Dyrobes rotor, there are 3 general categories of analysis: lateral, torsional, and axial vibration. Unlike other rotor dynamics software, with Dyrobes you can run all your analyses from the same model. Each category gives you many options of analysis to choose from. For instance, in lateral analysis, you can analyze critical speed, whirl speed, stability, and many other options. Here we'll run a critical speed analysis. You have 3 post-processor options to choose from. You can look at the mode shapes, the energy distribution, or the modal stress. The post-processor results give you valuable physical insights through colored graphs, charts, and illustrations. Here is the critical speed mode shape, modal stress, and displacement. You can see the large displacement in the overhung blades on the left. The colors of the graph show you where the maximum stresses occur in the system. You can also animate your results, which can give you additional insight into the dynamics of your system. And here is the energy distribution in the system. Here you can see that almost all the energy resides in the shaft and just one of the three bearings. With the post-processor, you can determine whirl speeds and critical speeds, instability thresholds, and eigenvalues. There are many options to choose from. For example, in the steady-state synchronous response category alone, there are 12 selections. For example, the Bode plot will show you the amplification factor. Here you can see that the amplification factor is 2.02, well below the 2.5 defined by the API standards. So in this case, it's not a problem. Now let's take a look at some of the torsional analysis functions. Here is a model of an engine driver gearbox, complete with a coupling and a compressor, which is typical of the kind of system you would want to analyze for torsional vibrations. In the torsional axial menu, you have several general options to choose from. You can input linear connectivity, nonlinear couplings and connections, modal damping factors, steady-state excitation, time-dependent excitations, startup transient analysis, and you can model torque in reciprocating gas or diesel engines. As with your lateral vibration analysis, you can run a torsional modal stress and displacement analysis which is color-coded to locate areas of high torsional stress in your system. You can look at the harmonics across rotational speed of individual elements or in the entire system. You can also review torsional natural frequencies across rotational speed with Campbell diagrams. Again, you can animate your torsional models, which will give you valuable physical insight into potential problems. Here, in the first mode, or critical speed, you can see a large opposing movement in the coupling, which indicates high torsional stress. It's important to note that in Dyrobes Rotor, you also have a variety of tools to evaluate aerodynamics, couplings, ball bearing stiffness, seals, and much more. Now, let's take a look at Dyrobes BPerf. BPerf complements Dyrobes Rotor by calculating bearing steady state and dynamic performance. Like Dyrobes Rotor, BPerf contains extensive modeling, analysis, and post-processing capabilities. The wide range of bearings that can be analyzed include fixed lobe bearings such as elliptical, multi-lobe, and pressure dam. BPerf also has programs for tilting pad, flexural pad, floating ring, gas, thrust, hydrostatic, and hybrid bearings. In addition to bearing analysis, BPerf performs lubricant properties analysis and oil flow calculations. It automatically calculates the effective film temperatures at operating conditions. In BPerf, it's easy to create a bearing model. You begin by selecting the type of bearing and by entering the bearing geometry. BPerf displays the results in text and graphics so you can understand your bearing as you build it. Here are the results of a pressure dam bearing with a center groove. The bearing stiffness and damping coefficients calculated from this analysis can then be easily output as a file used in your Dyrobes Rotor model and analysis. Once you have input all your dimensional analysis data, you can run the post-processor, choosing from many options. You can select Journal Equilibrium Locus to see how eccentricity is a function of RPM. To understand how pressure is generated in a bearing, you can also look at film thickness, stiffness, and damping. Or you can look at a 3D pressure profile. In addition to analyzing your existing bearings, you can also design your own bearings. Dyrobes lets you enter all the criteria you need. For example, to design this taper land thrust bearing, you enter the inner diameter, the inlet temperature, inlet pressure, rotor speed, and the bearing load. You also have many different lubricants to select from. Dyrobes automatically provides default data if you don't enter all the data. There are also many different tools to help analyze and design your bearings. With this example of a 4-pocket bearing, you can model and compare how different lubricants will work. You can compare viscosity, density, and ultimately determine the best oil for your system. There are also specialized design tools to address issues in specific types of bearings. For example, hydrostatic bearings are often unstable and produce cross-coupling effects at high speeds because of variations in pressure. With the hydrostatic bearing tools built into BPerf, you can monitor your pressure and stability as you adjust your bearing design. In this example, the pressure is controlled by designing a capillary tube or restrictor. And now let's look at the last two of the four Dyrobes modules, rotor bow and gear load. With rotor bow, you can perform multiplane balancing. With Dyrobes gear load, you can calculate the gear load effects on bearings. Inputting data into Dyrobes rotor bow is easy and intuitive. You can specify the number of balancing planes, the number of probes, speed, amplitude, and phase. You can position probes and decide which probe to emphasize. You can adjust the weighting and speed to determine your trim balance and unbalance. Rotor bow will show you the optimal weight to do the balancing. It even provides the influence coefficients if you require those numbers. And finally, with gear load, you can calculate the bearing loads due to gear and aero forces. Typical systems like this include a driver in the form of a motor or engine, which drives several high-speed shafts. To determine the loads, you input your pitch diameter, pressure, angle, and helix angle. Dyrobes gear load will show you the load on the bearing and the load vector. You need the load vector to properly orient your bearing. While the bearing itself may be fine, problems can result from a bearing that is not properly aligned. For questions and background, Dyrobes has extensive help menus for each of the four modules. Help files are indicated by the question mark icon. The help files are arranged by chapter and alphabetical index so you can find the theory and equations behind Dyrobes functions. You will find hundreds of diagrams and descriptions to help you develop your models and analysis. Rodyne Vibration Analysis is the official distributor of Dyrobes. To find out more, or for a free consultation, email us at info@rodyne.com, call us at this number, or visit our website, rodyne.com. Thank you.